We are leaving the world of solutions behind, and we are getting into thermochemistry. So this is a subject that you will look at now in chemistry, and then you'll hit the same subject again in physics next year. So this will come to you twice. You'll see a lot of these terms and a lot of these principles again. And actually, I think you even got a little bit of it last year in physical science. So by the time you graduate, you will know thermochemistry and thermodynamics really well. We're going to hit it now in the chemistry sense. So here are some terms that you will need to know. I'll give you a moment to write this down. So thermochemistry is the study of the interactions of matter and thermal energy, or heat. So we're going to be looking at when a chemical reaction happens. Does it give off thermal energy? Does it absorb thermal energy? Maybe it does a little bit of both. Maybe it absorbs some thermal energy and then releases some. And we're going to be talking about how a chemical reaction responds with matter and exchange the thermal energy. That's thermochemistry. Thermal energy is measured in joules, and a joule is a unit that you have seen once before. You saw joules back in physical science, back when the Earth was cooling 2 years ago, and you took physical science. The unit there should be familiar with to you. A joule is a relatively small amount of energy, so you will sometimes see energy expressed in thousands of joules or a kilojoule. This is a more usable quantity of energy for average things that happen. The total thermal energy of a system is called its enthalpy, and that's a weird word. Enthalpy is the measure of the amount of heat or thermal energy resident in something. So, you have a certain enthalpy, how much total thermal energy is in your body. And your total enthalpy is different than, some other objects, like this bottle, which has cold water in it. So it has a very low total enthalpy because there's not as much thermal energy in it. Enthalpy is the quantity, the total quantity of thermal energy resident in an object or in a system. And this weird word has a weird abbreviation. We use J for joule and KJ for kilojoule, and that makes sense, but H for enthalpy, that's not very helpful. There's an H in the word, but it's right in the middle, and you don't think of the word, or you don't think of the letter H when you hear the word enthalpy. So that's one of the things you just kind of have to get used to seeing, and I'm sorry, it's an H. I didn't make it up, but I guess E is already taken, so there you go. Thermal energy, which changes the temperature of a system, is called sensible heat. You can sense it when you add thermal energy to an object and it gets hotter. That is sensible heat. The opposite of that is something, not the opposite really, but a different kind of response to receiving thermal energy is thermal energy which does work or goes into a phase change. Then that's called latent heat. So, for example, I can take a piece of ice that is at -10 degrees Celsius, and I can heat up that piece of ice from -10 degrees Celsius to 0, and I have made the ice get warmer. And so that is sensible heat. The ice used to be -10 Celsius, and now it's 0. So sensible heat, I could have sensed that it is getting warmer. But then at 0 degrees, if I keep adding heat to that ice cube doesn't get any warmer. The ice cube starts to melt. And the heat that I'm adding to that ice cube is not going into making the ice cube warmer. It's going into turning the water from a solid to a liquid. And so that is latent heat. It's heat going in, but it's not raising the temperature. It's doing work on the ice or work on the water. So latent heat does work instead of raises temperature. Sensible heat raises temperature. Latent heat does work on the object or on the system that you're adding the heat to. So there is a latent heat of fusion, and there is a latent heat of vaporization. Okay? And so latent heat of fusion has to do with melting and freezing. So if you were to measure the amount of heat that it takes to melt an ice cube from 0-degree ice to 0-degree water, you would have measured the latent heat of fusion for water. And we would express that as delta H. Delta means change in. So change in enthalpy, change in the total amount of heat available in that system, right? Change of heat, and then we put FUS at the bottom as a subscript to represent heat of fusion. So this is the energy that it takes to melt something, or backwards, it's the amount of energy given off when something freezes, absorbed when something freezes. So the same amount of energy that it takes to melt 1 gram of ice at 0 degrees into 1 gram of water at 0 degrees is the same amount of heat that you would either absorb from the water or the water would give off when 1 gram of 0-degree water turned into 1 gram of 0-degree ice. So the phase change either direction has the same quantity. It gives off the same amount of heat when it melts as it absorbed when it froze. Just kidding, other way around. Gives off the same amount when it freezes as it absorbed when it melted. There you go. Now I said that right. So delta H FUS. Similarly, delta H VAP, the latent heat of vaporization, is the heat change between a liquid and a gaseous state. So the amount of heat energy that it takes to turn 1 gram of liquid water at 100 degrees Celsius to 1 gram of water vapor at 100 degrees Celsius is the amount of the heat of vaporization. And these are both latent heats because the temperature isn't rising, the phase changes, it's changing. Okay? And we always measure these in kilojoules per mole. How much energy does it take to move 1 mole of substance between the phase changes? So this is just an image of that. As ice gets warmer and stays ice, that's sensible heat. But when the solid ice melts into water, what we have here is 80 calories of energy going in to turn ice into water. But it's still at 0 degrees. This is water at 0 degrees, and so this is latent heat of fusion here. And then we can add 100 calories to raise that water up to 100 degrees Celsius. And then we can add 540 more calories to turn that water into steam, but still at 100 degrees Celsius. The vapor hasn't gotten any hotter. It's just turned from liquid water to water vapor. So this is latent heat of fusion. This would be sensible heat. This is latent heat of vaporization. Okay, and then all the numbers are exactly the same as you cool it down. If you took water vapor at 100 degrees Celsius and turned it into liquid water, that is condensing, and that is, again, latent heat of vaporization. The same 540 calories come out of it, and then you would cool it down and remove 100 more calories of thermal energy, and then you'd have water at 0 degrees, and then turning that 0-degree water into 0-degree ice, you would then remove 80 more calories. So latent heat of fusion is the same quantity, depending on which way you're going, and then latent heat of vaporization, same quantity. The sign just changes for which way you're going. Okay? Sensible and latent heat. You understand the ideas? Okay, dokie. And then, once again, the actual temperature does not change during a phase change. So if you have a solid that is very cold, you can heat the solid up, and as you add thermal energy, the temperature rises until you get to the melting point. And then when you're adding more thermal energy now, the temperature is not rising because this is latent heat that's just doing the work. Then it is liquid. You add more heat to it and the temperature rises. This is sensible heat. And then you get to the vaporization point or the boiling point and you keep adding more thermal energy, but this is latent heat again, and you're adding thermal energy while it's boiling. And then you get to the point where it's all steam or all vapor, and then as you add more thermal energy, you're now superheating the vapor. Okay, so latent heat does not change the temperature. Ice does not change temperature while it's melting. Water does not change temperature while it's boiling. All that more thermal energy you're adding just goes into the phase change. Take a moment, write that down.
So specific heat now. Specific heat, and we use CSP. And again, I don't know why it's C, great. H means enthalpy and C means specific heat. But CSP is a quantification of the amount of thermal energy needed to raise the temperature of the material. So certain things respond really quickly to additional thermal energy. If you put a copper pan on a fire, the copper pan gets hot real fast. And that's why we use, that's why copper is a great metal to use for pots and pans, because it transfers thermal energy really quickly, and it very quickly reaches high temperatures. But if you put water in that copper pot and put it on the fire, the copper pot is responding to the heat of the fire and passing a whole bunch of energy to the water temperature rises very slowly. The water temperature does not rise nearly as fast as the copper pot's temperature rises. And so water has a higher specific heat than copper. It takes more thermal energy to raise the same mass of that substance a degree centigrade. So specific heat has to do with how much energy you have to put into a material before its temperature starts to rise. Some things can absorb a lot of thermal energy and before their temperature goes up. Water is an example of that. Some things, their temperature goes up real quick, and copper would be an example of that.